Okay, so before we get started talking about mass spectrometry, I'd like to discuss degrees of unsaturation. And I think we've mentioned this briefly before, but degrees of unsaturation is also abbreviated as HDI, which stands for hydrogen deficiency index, or it could be abbreviated DU for degrees of unsaturation, or ring plus double bond for obviously the number of rings and number of double bonds in a molecule. And that's exactly what degrees of unsaturation represents. It means how many rings and how many double bonds do we have in a molecule. So consider pentane, for example. In pentane we have no rings and we have no double bonds. Here we have the molecular formula C5H12. Pentane is fully saturated, meaning that it has all of the hydrogens it could possibly have in the molecule. And so it fits the formula for an alkane, C sub n, H sub 2n plus 2, where n is the number of carbons. And so if we have 5 carbons, say, then we're going to have 2 times 5 plus 2, or 10 plus 2, which is 12 hydrogens for a fully saturated molecule. So here in 1-pentene, we're missing 2 hydrogens relative to the fully saturated molecule. So instead of 12 hydrogens, we only have 10. So we're missing 2 because we have a double bond. In 1-pentyne, we have a triple bond, so we have 2 pi bonds. So in order to form a pi bond, we have to be missing 2 hydrogens. So to have 2 pi bonds, we have to be missing 4 hydrogens, and that's the case here. Relative to the fully saturated pentane, we're missing 4 hydrogens. So instead of 12, we have 8. So our degrees of unsaturation is 2. So for every 2 hydrogens we're missing, we have 1 degree of unsaturation. So how do other types of atoms that we have in the molecule potentially affect the degrees of unsaturation? Where here we have a chlorine, so we have a halogen, and remember the bonding pattern for halogen is just 1 bond and 3 lone pairs. So let's compare that to the bonding pattern for hydrogen. So for hydrogen we have 1 bond, and for chlorine we have 1 bond. So obviously the other halogens are going to be the same, so like bromine and fluorine and iodine. So if we have any of these atoms on the molecule, it acts just like a hydrogen because it has the same number of bonds as a hydrogen, just 1 bond. So we don't really have to treat it any different than we would a hydrogen. But what if we had something like an oxygen in the molecule? Well, oxygen is just going to wedge itself between the carbon and the hydrogen, like in this case. So we don't really have to consider oxygens that are in our molecule. So, but something like a nitrogen is going to change that just a little bit. It's going to change the number of hydrogens that are in the molecule, because if we consider, say, for ethylamine versus ethane, here in ethane we've replaced one of the hydrogens with this NH2 group, so we have 1 extra hydrogen relative to the hydrogen that we plucked off on ethane to make ethylamine. So we consider that in our formula. So we can use this formula if we have a fairly complicated molecular formula to calculate our degrees of unsaturation or our hydrogen deficiency index. So our HDI is given by 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens, all divided by 2. Now most of the time you don't really have to use this formula to calculate your HDI. You can just compare the number of hydrogens you have relative to the number of hydrogens that would be in that molecule if it were fully saturated. We're going to work a couple of problems with that. So obviously if we have an HDI of 0, then the molecule doesn't have any rings or any double bonds. So let's think about what a molecule with a ring would actually look like. So let's take, say, cyclohexane. So what would be our formula for cyclohexane? Well, we have 6 hydrogens, so that would be C6. And what 6 carbons, I'm sorry, so that would be C6. And what about our hydrogens? Well, we have 2 hydrogens on each one of these carbons. So how many hydrogens do we have in this molecule? We have 2, 4, 6, 8, 10, 12. So that's C6H12. So let's compare that to the formula for a similar molecule that's fully saturated and doesn't have any rings or double bonds. So what molecule would that be? It would just be hexane. Okay, so 1, 2, 3, 4, 5, 6. Okay, so hexane would be C6H what? H14, because that would be C sub n, H sub 2n plus 2, and so 2 times 6 is 12, plus 2 is 14. So the molecular formula for hexane would be C6H14, so we have 2 fewer hydrogens in cyclohexane than we would have in hexane, and that's because we have a ring. So when we formed this ring, what did we do? Well, we had to pull a hydrogen basically off of each end and connect those carbons together. So if we pull off a hydrogen here, and then we can connect those carbons back together to get cyclohexane, right? We have to pull off 2 hydrogens. So for every ring we have, we pull off 2 hydrogens, and for every double bond we have, we also have to pull off 2 hydrogens. And that's why this is called a hydrogen deficiency index. So let's work a few problems with that. Let's calculate the hydrogen deficiency index for some of these molecular formulas. And I'm not going to work all of these. I'm just going to work a few of these problems. So let's take, say, 15.54a. So let's work A. For A, we have C4H6. Okay, well, what would be the molecular formula for a molecule containing 4 carbons that's fully saturated? Remember, our formula is C sub n, H sub 2n plus 2. Okay, so that would be C4H what? Well, 2 times 4 is 8 plus 2 is 10. So that'd be C4H10. But here we have C4H6. So 10 minus 6 is equal to 4. That means we're missing 4 hydrogens. Does that mean our HDI is 4? No, because for every number in our HDI, we have to be missing 2 hydrogens. So for every ring or every double bond we have to be missing 2 hydrogens. So we divide that number by 2, and that gives us 2. So our HDI here is 2. But we can use the other formula to calculate it as well. Our HDI is given by the formula 2 times the number of carbons plus the number of nitrogens minus the number of hydrogens minus the number of halogens plus 2, and all of that is going to be divided by 2. Well, this is a pretty simple formula, a pretty simple molecular formula here, so we won't have to use all of these potential entries, and so we can just say 2 times our number of carbons, which is 2 times 4. Okay, my tablet is not agreeing with me here. 2 times 4, right? And then we have our hydrogens, and that is minus 6, okay? Because we have 6 hydrogens, and now all of that divided by 2, and I forgot our plus 2 over here. Okay, so 2 times 4 is 8, minus 6 plus 2, all divided by 2, which is going to be equal to 4 divided by 2, which is 2. Okay, so we got the same number here and here. So if you have a simple formula like this, like C4H6, this is just a hydrocarbon. So you can just compare it to the formula of a fully saturated hydrocarbon that would have the same number of carbons in it, and just subtract the hydrogens and divide that number by 2. It's very quick and easy to do it that way. Okay, so let's work another problem. Let's do E. Okay, so here we have an oxygen. Remember, oxygen doesn't affect our HDI, so we don't have to consider it in the formula. Okay, so remember our formula is, in fact, I think I'm just going to write our formula right here so we won't have to rewrite that every time we use it. So our HDI is given by 2 times the number of carbons plus the number of nitrogens minus hydrogen minus halogen plus 2, all divided by 2. Okay, so if we work E, okay, then we have C6H6O2. So that's going to be equal to 2 times the number of carbons, which is 6. Okay, and of course that would be in parentheses because we multiply first, right? Minus 6 for a number of hydrogens plus 2, and all of that divided by 2. Okay, so that's going to be equal to 12 minus 6 plus 2 divided by 2, which is equal to 8 divided by 2, which is equal to 4. Now, how would we calculate that if we want to do just this quick and dirty way of doing it, where we would consider our formula for the fully saturated alkane? Well, remember, it's C sub n H sub 2n plus 2. Okay, so we have 6 hydrogens, so that would be C6, and then H2n plus 2. 2 times 6 is 12 plus 2 is 14, so H14. Oxygen doesn't affect our hydrogen deficiency index, so C6H14 relative to C6H6. So we're missing that many hydrogens. We're missing 8 hydrogens, right? And so we can kind of skip over to this step and say we're missing 8 hydrogens, and then we divide that 8 by 2, and that gives us 4. So our HDI is equal to 4. Okay, so let's go ahead and do another one. And let's do, let me see, how about F? Oh shoot, I erased my formula. Oh well. Okay, so F has a nitrogen in it. So nitrogen is going to affect our formula a little bit. And how is it going to affect our formula? We have to add a hydrogen on before we divide by 2. Oxygen doesn't affect our formula, so let's see what that will look like. So our HDI is equal to 7, which is the number of carbons, times 2, okay, minus the number of hydrogens, which is 9, okay, plus the number of nitrogens, which is 1, because we have 1 nitrogen, and then our oxygen doesn't affect the formula, and then plus 2, and all of that divided by 2, which is equal to 14 minus 9 plus 1 plus 2 over 2, which is equal to 8 over 2, which is equal to 4. So our HDI again here is 4. So for nitrogen, you might want to go ahead and use your formula so that you can calculate this, you know, without getting confused or messing up or something. So what does that mean? It means we have 4 rings and a combination of 4 rings and double bonds. Okay, so we could have different types of formulas, but we have a combination of 4 rings and double bonds. That's all we can say from that. So why don't we write our formula back up here before we do the next one. So, So our HDI is equal to 2 times the number of carbons plus the number of nitrogens minus the number of hydrogens minus the number of halogens plus 2, all divided by 2. Okay, and our formula for a saturated alkane is C sub n H sub 2n plus 2. Okay, so let's do another one. Let's do I. It has a halogen in it, and see how that affects our formula. So the formula for this molecule is C sub 6 H5Br. Let's calculate our hydrogen deficiency index. Our HDI is equal to 2 times the number of carbons, which is 6, okay, minus the number of hydrogens, which is 5, minus the number of halogens, which is 1, plus 2, all over 2, which is equal to 12 minus 6 plus 2 over 2, which is equal to 8 over 2, which is equal to 4. Wow, this is 4 again. So we have a lot of them that have 4 as a hydrogen deficiency index. And let's think about this a little bit further. Remember, bromine has the same bonding pattern of a hydrogen, so that would have the same HDI as a molecule that was C6H6. Let's compare that to the relative fully saturated alkane, which would be C6H2n plus 2, so that would be 2 times 6 is 12 plus 2 is 14. Okay, so 14 minus 6 is 8 divided by 2, which is 4. So we could quickly get our hydrogen deficiency index in that way. So I'll let you guys work the rest of these homework problems for yourself, and my next video will be covering an introduction to mass spectrometry, which is section 15.8 in the Klein textbook.